Hello, it's James here. This is a video about other types of linear actuator. So a lot of people have asked me about openDog, which of course is an ongoing project in the series, where I've used brushless motors and oDrive Robotics brushless motor driver and ball screws to actuate all the joints. A few other people have asked me about, could we make this smaller, could we make it lighter, cheaper, lower power, and so on. And it struck me it'd be quite good to have another solution for doing other robotics projects to make a linear actuator we can put across joints, because generally lead screws and ball screws are fairly low backlash, so it's a good way to gear the motor down. So today we're going to look at a much sort of smaller, more common, cheaper solution using DC motors with encoders. So just to recap on this project, but check out the series for the entire construction. I'm using these big brushless motors, which are turning G aero drives. The 149 kV, the 6374, these peak at 2 kilowatts, although they're currently limited to 30 amps and 24 volts. We can go higher. These are driving ball screws, which are these 1605 ball screws, which have a 5mm pitch, and they are 16mm in diameter. So they're an incredibly powerful solution here, with a 2-to-1 ratio for driving this motor. But the only reason they need to be powerful, and they're probably over powerful, is that most of the weight of the robot is in fact the motors and the ball screws, because they're made of steel and the motor's full of copper wire. So there are 12 of these, and picking those up in a box when all the parts arrived, pretty much we could see the robot was going to be pretty heavy before we'd even started. Tucked away in each end of the robot there's 3 oDrive Robotics brushless motor drivers, so 6 in total. Each one is a dual motor driver which will drive 2 motors. So these are pretty much the only solution at the moment to accurately driving those brushless motors. Each motor's got an encoder attached, and not only does the oDrive use that for effectively energizing the motor coils depending on the stator position, it also does velocity and position control using that same encoder. openDog is an open source project, so you can download the complete CAD assembly and all the code and build your own, although I don't recommend you do until I've got significantly further on with the series, because at the time of making this video it doesn't actually walk yet. So a few people have asked me about, could they make a cheaper version, maybe half the size? And a curious thing happens when you scale things up and down, because of course if we were to make it half the length, we'd also be making it half the height and half the width. And so actually we end up with 1/8 of the volume. And you can see this by stacking up cubes. Of course, if you extend something in 3 dimensions, it's a cubed function. So if you were to double it in size and double it in height and width, you're actually extending all 3 dimensions. And if you took all those parts and just scaled them up, it would be 8 times the mass, which means you'd get 8 times more powerful motors, batteries and everything else. So we're going to talk about the other case where we scale it down a few factors, and of course it means we don't need motors that are half as powerful, we need ones 8 times less powerful. So that means we can use some cheaper off-the-shelf parts that are probably a bit more accessible to people on a budget. So we're going to be using a DC motor. This is a motor made by Polulu in the US. There's a European reseller called robotshop.fr where you can get these in Europe. I think this was about £36 or something like that. It's a 30-to-1 motor, does about 300 RPM or 350 off load on the output. It's about 36 or 38mm diameter motor, fairly common motor size, and this one's got an encoder, so it's got some extra wires that poke out the back. It's got a 64 counts per revolution encoder on the back on the actual motor, and of course it's 30-to-1, so that gives us 1920 encoder counts on the output shaft. Now the encoders I'm using with the oDrive on the brushless motors are 8192 encoder counts per revolution, so this isn't quite as accurate, but obviously probably good enough for our purposes. And I'm going to be using lead screws as a more compact solution. You can get smaller ball screws, but they tend to cost quite a bit. The 1605s are fairly common on eBay. The ones I had there were £23 each on openDog. These things are much cheaper because there's no ball in the nut, it's just a nut. And this sort of thing you find on the Z-axis of 3D printers. So we're going to drive those with the motor and make a linear actuator out of that. So I've got some bearings and things to mount them in there, and we're going to mount that up and mount the motor with a coupler, and that's going to be the solution for positioning and hopefully velocity control in this demo. We could of course make this more compact in the same way I did with openDog by putting the motor next to the lead screw and running a belt or a gear between the two. In this example I'm just going to stick it on the end there with a coupler, because I don't really care how compact it is, but it could be quite a compact actuator. If we had this lead screw quite short, we could fit it in quite a small envelope, perhaps to make the bicep or some sort of other joint in a humanoid robot torso on some sort of project like that I'd like to do in the future. So of course, being just a normal DC brushed motor, there's no reason to have any specialist motor driver, but we do need something to handle the current. So I've got an IBT4 here, which are about something like £10 on eBay. You might get away with something smaller. These are about 20 amps, which is excessive even for this motor. And of course we can read the quadrature encoder on the back of the motor with 2 interrupts on an Arduino Uno, which we'll come on to shortly, and then we can drive the motor and then we can position it. So I'm just mounting that lead screw up on a 3D print each end with a bearing shoved in each side, an 8mm internal diameter bearing to match the screw, and that sits on my 2020 quite nicely. I've got these little collars which have got a grub screw in made of steel. I got those off eBay just to stop the lead screw obviously slipping in the bearings. So of course as we turn the lead screw, the nut will travel up and down, and we can stick the motor on one end. Now this is just a little saddle that stops it swiveling round. So that's sitting either side of the 2020 there. Isn't really the proper way to do it. What we should probably have is some sort of supported thing that actually stops sideways load on the lead screw from bending it. So you could use something like this V-slot extrusion with wheels that run up and down, which is how some CNC axis work on some machines. Or you can of course get recycled ball bearing sliders. You can get some really tiny ones. Probably should have bought something for this video, but for now we're just going to remain unsupported and mostly concentrate on how we position it using code. Of course I've got a coupler to attach the motor to the screw, so this whole assembly is getting quite long. As I said, we could double it round and use a belt drive, which is also quite forgiving because there's some flex in it. This is one of these aluminium ones that's slightly flexible to keep alignment without putting any load on the motor. So of course we just need to do up the grub screws there, and that will drive the lead screw as the motor turns. So of course it's a DC brush motor, so if we put power on it then it would make the linear slider work, but in fact I can back drive this one because it's low enough gear ratio. So we can see the lead screw working and of course the nut going up and down. So the first thing we're actually going to do is work out how we read all the encoder cables into an Arduino. I've just used a bit of pin strip, a bit of right angle shoved into the connector that comes with that motor to extend the wires out. The red and black are the ones that go to the motor driver that power the actual motor, so they're not attached to anything for now. And the other 4 are to do with the encoder. So I dug around for the data sheet. I eventually found that on Polulu's website that tells you what the 4 wires do. I've used the same colour wire to extend them, apart from I didn't have any green wire, so it's this grey and black wire. But basically the green wire is the ground for the encoder, which goes to a ground pin on the Arduino. The blue one is 5 volts or 3.3 to 5 volts that actually powers the encoder. So I've taken that onto a 5 volt pin on the Arduino. And the other 2 are the encoder signals A and B. Yellow is A and white is B. So I've wired those to pins 2 and 3 on the Arduino, which are the interrupt pins. And we've got 2 signals coming out of this encoder, so we can work out which direction it's turning. And basically pins 2 and 3 are interrupt pins, so that means that we can run code when that pin state changes, and we can accurately count those encoder counts. It will actually interrupt any other code running, so we don't miss any of the counts. There's quite a lot of rotary encoder code out there, so I'm actually looking at the Arduino playground about using rotary interrupts, and we're using this example here, which I think is example 2, which uses 2 interrupts and interrupts the processing to give you the number. So this is the actual code. It's fairly small writing, so let's have a look at it here where I've actually made a working sketch. So of course I've put the link there to the Arduino playground, and I'll be publishing this code so you can have a look yourself. I'm running my main loop every 20 milliseconds, which is what goes on down here, so that's what these variables are. And most of this is just setting up the pins here, so we're defining pins 2 and 3, saying their input pull up, and this bit of code here is attaching the actual interrupt. So interrupt 0 is pin 2, and interrupt 1 is pin 3, and we're saying those are pin change interrupts, so to run code whenever those pins change state. In my main loop, there's virtually nothing. It's just running the multitasking thing, so it runs every 20 milliseconds instead of as fast as it possibly can. And all it's doing is actually printing the encoder position. And what happens with interrupts is when you interrupt the pin, you define a function that's basically tied to these pins. So do encoder A and do encoder B are functions, and those sit right down at the bottom. So each one of those is checking if encoder A pin is triggered first, or if the encoder B pin is triggered first, and then what happens after that. And that's how it determines which way the encoder is turning. So if it's turning one way, it adds 1 to the position, and if it's turning the other way, it takes 1 away from the position. And it does that in both cases, depending on whether encoder A pin or encoder B pin is triggered first. And of course this interrupts any other code, so it's really accurate. It stops anything else running. We haven't got anything else yet, but we will have later on in this video, so we shouldn't miss any encoder counts. So now if I move the motor, we should be able to see the encoder counting up in one direction and counting down to the other direction with 0 in the middle. So that seems to work all right. We can put some power on the motor just with a battery now, and we should be able to see the same effect. So that gives us the maximum and minimum for that actuator. Unfortunately, it's under 32,000, which is the maximum value for an integer, so we don't have to use long variables. I've now wired in the motor driver to the Arduino so we can control the motor with the actual Arduino code. So we've got the battery goes in there, the red and black to the motor go into the motor, and this one's got 3 pins. It's got a ground pin and an in 1 and an in 2, and the 2 ins are there for turning the motor in each direction. So the ground pin is attached to a ground on the Arduino, and the 2 ins are attached to 2 PWM pins, which are pins 9 and 10. If we stick a PWM signal into one and 0 into the other one, the motor will turn one way, and so on the other way round. Right, I've now implemented the Arduino PID library, which I use in quite a lot of projects, and again that's from Arduino Playground, and that will allow us to match a set point position, which is basically demand, against the actual input position, which is the actual position of the encoder in this case. And it'll move the motor accordingly to try and remove that error to 0, which is quite good for control. And we can tune that with various variables. The P, I and D, in this case I've just put in some variables that work quite well for P and D, I haven't done I, and that's perfectly acceptable for motor control generally. You can read quite a lot about PID controllers on Wikipedia, but generally I just tune manually. So that's the setup for the PID driver. In setup we also set up the maximum and minimum output, which is -255 to 255, and that's because that's the most we can put into the Arduino PWM. Now in our main loop we've just added the ability to do a serial read, so I'm going to actually send that set point demand position by typing in numbers. So what I'm doing is a parseInt to read a number, and I've also got a character after that, and I've set that character so that it only updates the variable for our set point if it's A. We could have multiple of these, all on different, say, Arduino Nanos or Pro Minis, lots of actuators in a robot. Each one could have a different identifier, so it would only actually update the variable when it saw its identifier. So we can have one would be A, one would be B, one would be C, and so on. In this case, there's only one, but I've put it there for good measure. So our input for our PID controller is the encoder position. Our set point is that read value that gets updated when there's serial data. We do a PID compute, and I've written those variables out to this terminal, which we'll have a look at in a minute, and then we drive the motor. So if the value that comes out of PID is positive, it drives one PWM pin with that value, and if it's negative, it drives the other one. Now this ABS statement just always turns the negative round to be positive. Of course we only need to put that on the one where the value is less than 0, but it's there for good measure. And obviously if the value is not bigger or smaller than 0, it must be 0, so it turns the motors off. So now I can put values into the Arduino with an A on the end, and it should move the motor. So let's go for 5,000. There it goes, and you can see these values updating. So we've almost hit 5,000 on the encoder there. We've got 4977, which is pretty close. We could tune up that PID controller a bit better, but that's good enough for an example. And this is the actual value that's being written out of the PWM. So obviously we haven't quite got to it. We've got 8 left. Don't know if you can hear that motor buzzing, and that's purely because it's not quite there and there's not enough power to move it. So could do with some better tuning there, but let's do -5,000. And we should see a similar thing there. So I think we can get to 15,000 before we run the end stop. And you'll notice that PID control is quite good. It decelerates so it doesn't overshoot, because that's the proportional part of it. So it should decelerate as it gets to the middle or the end or whatever the target is. And that seems to be working pretty well at the moment. So that works pretty well. We've got position control that's pretty accurate if you think about how many encoder counts per revolution, and we're there with ±10 with not much tuning. It could be made stronger, it could be made faster with a different pitch lead screw and of course different gear ratio on the motor. But there's one feature we haven't implemented. On the O drives we've got the ability to actually control velocity regardless of what happens to the battery. If the battery goes flat or the motor's more loaded, it will still try and maintain velocity, counting those encoder counts to count the velocity of the motor. So how are we going to implement that on here? So what's velocity? Well, velocity is just a change over time. So if the encoder position changes more over a set period of time, it must be going faster. So that's how we're going to work out velocity. So I've just added 3 lines of code here. It's pretty easy because we know that our code loop is running every 20 milliseconds, so we can just measure the encoder change in that period, and that'll tell us how fast it's going relatively. So we've just got 2 lines of code here really, as well as putting that out, and we're measuring the difference in position of course between cycles. So the second statement is bookmarking it, saying what's the previous position is equal to the current encoder position, and then the loop of course goes round, comes back to the top, and by the time it's got there, there's been some change, so it then works out the difference in position by taking one away from the other, then it bookmarks it again, and then we're just printing that out to the serial terminal. So if we open a serial terminal, it's the middle column now, in fact, so if I were just to turn that manually, you should see it ramp up as I'm moving it, and come back to 0 at the beginning. So there we go, when it's not moving at 0, the faster I turn it, the higher the numbers should get. So let's power this up now, and I can just do this as well by putting in a value and driving the motor. We should see a high value and then see that middle column coming back to nothing at the end. So now we know what the motor speed is, we can use that as another input on a PID controller, and then we can define how fast we want it to go with another set point. So I've now set up a separate PID controller called PID2. The first one of course controls position, and the second one tries to regulate the velocity of the motor. So of course we've already done the reading of the motor speed, but we need something to set it. So on my serial read, I'm now reading a second value called read2, which is going to be the velocity, and we'll type those in on the serial terminal. If of course the identifies A again, then it sets the second set point to that value. So our input 2 is the difference in position between the encoders in the loop, which is essentially our velocity. The set point of course is that value we specify. So I do a PID2 compute, and then I'm going to use this value that comes out, the output, essentially to regulate the maximum speed that the first PWM can send the motor. Of course it needs to go slower so that the motor can decelerate proportionally so it doesn't overshoot, but it shouldn't go faster than the speed we set. And so all I've done is put a constraint in each of these motor driving bits of code here that basically constrains the value we're outputting to a maximum between 0 and a maximum of the value that comes from the second PID controller. And of course this code loop runs every 20 milliseconds, so the value is constantly updated by the first PID controller and by the second one trying to regulate the speed to its maximum. So now we can set the velocity as well as the position of the motor. So if we give this 10 thousandths and we give it a velocity of 255, then off it goes at full speed. And if we give it minus 10 thousandths and we turn that speed down to 150, we should be able to see that going slower. And that works all the way down until the motor hasn't got any power to turn anymore. So let's just go to 5 thousandths and we'll try to 80. And you can see that is in fact going slower. So that works pretty well. The important thing though is that it could actually regulate the speed, so that if I put it on load, then of course we should find that it should get quicker. So if we take this to one end here and then take it all the way back, now it's important to say that we have to run this less than the maximum, because if it's running at the maximum speed, there's no overhead, there's no way to turn it up. So of course we're going to run this at 150 or something, and I'm going to try and load the motor, and you should see that the motor's still turning at roughly the same speed. Now this is down to the tuning of the PID controller. You can hear it struggling, but that's just burnt my hands off. So it should be using that second PID controller to turn the speed up, so that in fact it still runs at the same speed by just uplifting the maximum PWM that the first PID controller can drive into it. So I have to stress that this is nothing like an O drive. The O drive is very good at positioning brushless motors accurately and controlling their velocity. This is really just a budget example if you don't want to go to the expense of buying O drives. Otherwise my recommendation is use the O drive anyway. Just use smaller brushless motors. You could still use a lead screw or a smaller ball screw, because that's probably the most efficient way to get the good power to weight ratio out of the brushless motor, which is phenomenally better than a DC brushed motor. This example is really if you want to do it on a budget, you're going to scale down a robot, this one or another one, and you need to implement lots of motors that are positioned accurately, and you don't want to spend lots of money. It still adds up a bit with the motor and the motor driver, but these are all off-the-shelf things, Arduinos and motor drivers you can get off eBay cheaply. Obviously I haven't calculated any forces, I haven't worked out what scaling down the dog would mean in terms of forces on its joints, so if you're going to try and build it or a similar robot, please take this and prototype it, try out different motor gear ratios, try out different lead screw lead ratios, which is essentially part of the gearing, build a prototype leg or whatever you're building on the robot, try holding it back with your arms and check that actually there's enough force. I've put all the Canon code in the link in the description in this video, which basically is open source or preserves the original licensing from Arduino Playground, so you can check that out. And don't forget, there's going to be more on openDog coming up. We still need to make it walk. So don't forget to subscribe for more updates on this project and all the other projects. And also don't forget to check me out on Patreon if you want to support the channel. And you can also get my merchandise as well. We've got openDog t-shirts, mugs, stickers, and various other things that you can get in the link from the description below. Alright, that's all for now.